three objectives as we consider the derivatives of polynomials. First, we'll define what we mean by the derivative of a function very informally, and then consider a particular polynomial and note that the coefficients in the equation of the polynomial must have units, and we'll need to be able to figure out what the units are on each of the coefficients. And then lastly, we'll apply the rule for taking the derivative of a polynomial. So suppose we have some position versus time function here, and I would like to find the average velocity over some time interval delta t. So let's say starting from here to there. Let's note this time interval, call that delta t right there. The average velocity of our object during this time can be found from this definition here. Average velocity is delta x over delta t. Let's see, that's our definition here from integral over interval. So delta x over delta t, we note that that is equivalent to, graphically, the slope of the secant line connecting these 2 points. So I'll draw in the secant line here, intersecting the graph a couple of points. And if we make that the hypotenuse of a right triangle, with these legs of length delta x and this leg delta t, that's delta x right there, then the slope is delta x over delta t, which is exactly what we mean by the average velocity. Okay, now consider what happens if we look at a shorter time interval, say from this time to this time. So we'll shrink our time interval, consider from here, or from this time to this time instead, and look at the secant line between those 2 points on the graph. So over that time interval, this delta t, that delta x. Okay, we have a shorter delta t here and a different delta x. So we have a slightly different slope here. And I want to consider what happens if we continue to shrink that interval delta t. If these 2 points on the graph get closer together, and so close together that they merge. What if we let delta t go to 0? Then our secant line would eventually become the tangent line. If we let those 2 points sort of get closer and closer together until they merge, then we'd have a line that intersected the graph at just 1 point, that touched the graph just at that 1 point there. That would be our tangent line. And what we'd be talking about then would be the instantaneous velocity. So if we took the limit as delta t went to 0 of your average velocity, so finding the average velocity over a time interval that shrunk to 0. So that would be the limit as delta t went to 0 of delta x over delta t. And this is a lot to write, so we have a shorthand for this. Instead of writing this limit and all these deltas, we just express it like this instead. So this is our notation that expresses this, dx over dt. And this is our shorthand for the slope of the tangent line. So in the limit that the secant line becomes the tangent line, the slope of it, which was the average velocity, becomes the average velocity over an infinitesimally small interval. That's what we identify as the instantaneous velocity at that particular time, t naught. So the slope of this line is the instantaneous velocity at t naught. Regarding this dx and the dt, by that notation, dx means an infinitesimally small delta x. Dx is a tiny displacement. So since a displacement has units, the SI unit would be meters, dx has units as well. Dx has units of meters. And dt is an infinitesimally small delta t. This just means like a very short time interval. So it also has units. So dx has units of meters, dt has units of seconds, so this what we call the derivative here of x with respect to t has units of meters per second, and that's our units for our velocity right there. The point I'm making here is that by this little d that we use all over the place in calculus, d just means a very tiny delta. D for delta, an interval that has shrunk almost to zero, an infinitesimal interval as small as we can possibly imagine. And so the slope of our tangent line here can be imagined as our tiny delta x, or rather our tiny dx, over a tiny dt. There's no way to draw it small enough here. We just have to imagine an infinitesimally small little change in x, we'd call that dx, over an infinitesimally small change in time, we call that dt. Tiny dx over dt, that's the derivative, that's the slope of the tangent line. That is our instantaneous velocity.